Wonderful. We got three good seats up here in the front for those people standing in the back. You might as well come now, you'll get tired. So I want to explain something about it. First of all, I'm going to play three roles today. The first role is Emeritus Professor Donald Knuth from the 21st century. And that role, I'm going to be standing right here. Then I'm going to briefly play the role of George Forsythe, who was chair of the computer science department in 1969. And when I'm George Forsythe, I'm going to be standing right here. Okay? Now, George is going to introduce tonight's speaker, who is a young, 31-year-old guy named Don Knuth. And that young guy is going to be, when I stand here, that's who I am, okay? So hope you can understand it. All right, now, this whole thing started, Stanford has a project going on for some years called Class X, and the people, the idea is to make interesting videos to put on YouTube for the future, and so that things that are going on these days at Stanford can be appreciated by people in future generations. So they asked me, would I be able to tape some kind of a presentation for the future? And I said, well, I think it would be fun to do something different, and that would be to try to repeat the first lecture that I gave after I'd become a professor at Stanford. This was, I had just become my title changed from mathematician to computer scientist and so on. And at that time, as you see, I wanted to explain what it was that I expected I might be doing the rest of my life to the people around. So that's the beginning of this talk, and it was November 4th, 1969. That was a Tuesday, and I, in order to be a little bit authentic, I went over to the Gap and I found out that they are selling 1969 blue jeans. So I bought myself a pair of blue jeans. Okay, and also, believe it or not, I'm wearing a wig. The reason is just to help me remember that when I do give the lecture, that I speak as much as I can, as I would have spoken in the 60s. Now, if you want to see what I really looked like, in the lobby of Gates Building, the first floor, there's a really nice historical display. It shows pictures that were taken, of John McCarthy, Ed McCluskey, Ed Feigenbaum, and so on, a lot of it Bob Floyd, and also you can see some of the students who were riding and trying to tear down the computer center and so on. But anyway, this was the 60s, but actually most of the action of the 60s took place in the 70s, but it was early 70s. Anyway, so 1969, I also put online some home movies that my wife and I took in the 60s, in case you're really interested in seeing what our cat looked like in 1969. All right, so now in order to prepare for this, but by the way, I came to Stanford because it was the world's greatest computer science department by far, by any measure. And I mentioned George Forsythe, the chair. Well, he had worked very hard all through the 60s to build up this department, and the department actually opened in 1965. And so this was the place where I could come and be have all the great professors in one place instead of having to be isolated somewhere else. So now, in order to get ready for today, I went to Stanford Archives, where George's appointment calendar was, and so I could look at faculty minutes of faculty meetings and so on, figure out what's going on. I, I want to mention, by the way, also that George, if anybody deserves the name father of computer science, it's George Forsyth. So this is also everybody loved him, and it was everything that's good about Stanford Computer Science now is pretty much due to him. So then I also looked at the Stanford Daily for November 4th and a few other days. And so what was the big news on November 4th? That morning, it said essentially the previous night, Monday night, the campus was quiet for half an hour while all the students were listening to President Nixon giving a special address about Vietnam. And evidently what Nixon said was that he had a secret plan which was for winning the war in Vietnam. So this was, this was not too well received on campus because the vast majority of the students wanted the Vietnam War to be over with, and Professors Sandy Dornbush and Martin Pearl were leading a movement called the Vietnam Moratorium Movement and so on. So there's lots of stuff going on, but that still hadn't heated up very much at this time. We were still going to classes and thinking about science and things in those days. Okay, so that's trying to set the scene from then. And I guess then my next thing is then to be George and introduce tonight's speaker. Okay, people in the back, come up in front, have a seat. Welcome to our weekly colloquium. I'm happy to announce that we'll be able to meet again in Polio Hall starting at the end of this month. Now tonight, this afternoon's speaker is one of our own. I'm really happy to introduce Don Knuth, who joined our faculty a few weeks ago. And I know some of you know that he's teaching our introductory class 136, which is going to become 106 in the future. You probably also know that he wrote a book called The Art of Computer Programming. In fact, the first volume came out last year, and the second volume came out this summer. And I've been told that his books have set a new record at the Stanford Library, that no other book in the history of the library has been stolen so often from Stanford's library. So now he's going to give a talk about a kind of a strange topic called the analysis of algorithms, so I'm looking forward to hearing what he says. Don. Thanks again. Well, wow, I'm really happy to be here, and at last I can officially call myself a computer scientist. So this is my, solves my identity crisis, and I can become part of the terrific faculty that we have here at Stanford. In fact, even more important than the wonderful faculty that Stanford has is our students. I think it's quite clear that we've got absolute best students. In fact, in this room this afternoon, probably we got a substantial fraction of the best computer science students in the whole world. And I'm especially happy to be also here to work with my longtime colleague Bob Floyd. Although previously we've done all our work by mail and writing letters back and forth frantically. So at last we're going to be able to work together as colleagues and face to face. Now, George asked me to give a talk that sort of introduces what I do, since this is the first time I'm talking, here in public at Stanford after getting this appointment, and it reminds me that earlier this year, my colleague Klaus Wirth, I'm sort of Klaus's replacement here, because Klaus was called to be professor at ETH in Zurich. And so Europeans have a wonderful tradition of the inaugural lecture. And it's kind of a big deal. The professor's first lecture in Europe is reported in the newspapers and so on. Now, I'm not going to give a talk that's going to get reported in any newspaper. In fact, it's kind of depressing to read newspapers these days anyway. But I do want to give a talk that could be considered in some way an inaugural thing, because the subject is really what do I sort of view as what I want to work on while I'm at Stanford. Is there some general theme or something that underlies it all? So so much for that. Now I have to actually speak again from here. Unfortunately, Emily's boss decided that Class X was such a classy project, it wouldn't be good for me to wear a wig throughout this whole presentation, because you know, Stanford is a very serious institution, and so you know, and so I don't want to get Emily in trouble with her boss, and so it's too bad. However, I can't take the sideburns off. They're sort of locked on. So maybe that'll be enough to remind me that you know, that I'm speaking from the 70s. Okay, now let's go back then. So what is this? What is this strange title, the analysis of algorithms? Well, I can explain that, but actually it goes back to a story. A couple of years ago, I was at a conference of mathematicians in Santa Barbara, and somebody asked me at dinner, "What do you do?" And I said, "Oh, I'm a computer scientist." And computer scientist? Oh, are you a numerical analyst? And I said, "Well, no, no. You know, I like numbers and stuff, things like this, but I'm not. Numerical analysis isn't quite the description of what I do." So I said, "Oh, artificial intelligence?" And I said, "Well, no, not really that either." And so the guy says, "Oh, then you must be a language man." Now, you see, in those days, computer science consisted of three possible things. One was numerical analysis. One was AI, artificial intelligence, and the third was programming language, the study of languages, formal languages that are used to describe algorithms. Okay, but it occurred to me that really I wasn't in any of those categories, and so I had no way to explain what I do, what I did. And so that night I started thinking about it and said, well, wait a minute, I've got to have a name for what I like to do. And so I came up with saying, okay, the next time somebody asks me what I do, I'm going to say analysis of algorithms. I didn't really know exactly what it meant at the time, but I knew that I needed a name for it, and I figured, you know, Richard Bellman made up a name, dynamic programming, and everybody got to start using it, and so I figured if I started, you know, talking about it long enough, it would become, you know, a well-known discipline. But anyway, I did know that what I liked to do was analyze algorithms. I mean, I like, you know, algorithms. I don't have to explain to you guys what an algorithm is, a procedure. But I want to quantitatively study algorithms and not just qualitatively and so on. Again, so I'm going to explain to you by example. I still haven't really come up with a perfect definition of what it means, analysis of algorithms. But by example. I mean, the working definition is whatever I'm interested in is analysis of algorithms. But I intend to refine this over the years. But by giving an example, I think I can explain to you what is sort of special about it. So let's take an example. I want to I'm going to work a simple algorithm so that we can sort of analyze it to the hilt. And here we go. So the algorithm is going to be to find the maximum of n numbers that are given. Okay, so x1 through xn, got to find the maximum. Okay, so here we go. Start out, come in here, and the first step is I set m to x sub n, and I set k to n minus 1. All right, that's the very first step. After that, I make a test. Is k equals 0 or not? Okay, so sorry, I haven't developed my skills at writing good zeros on the blackboard here. So I've got two variables here, m and k, and I start out and I that way, and so it might be that k is equal to 0, and then I'm going to come do that. But if k is not 0, then I've got to make another test, and I'll write that down. So that's is xk bigger than m? And again, it's yes or no. And so I'm going to put this algorithm down, and then you'll see. Then we'll play through it, and you'll understand exactly what it does. So the yes is saying m replaced by x sub k, and no says k is set to k minus 1, and these come about here and go all the way back. And so I got the algorithm out here, except for what happens under yes, and at the end here it says output m. And we're done. Okay, so this is, I think if anybody here has written at least half a dozen programs, they probably came up with a loop somewhere in one of those programs that's very much like this. Okay, so it should be fairly familiar, but let's take an example and play through. So suppose that n is 4, and x1 is say 2.3, x2 is 7.1, x3 is 4.0, x4 is 5. By the way, if anybody has a question on what I'm saying, stop me right away. I want to know, unless you don't understand anything, and then you can't ask anything. But anyway, ask me, and I'll try to answer. It's your chance. Okay. So we start out, and the first part of and we set m is going to be set to 5.9, which is x4, right? xn is 5.9, and k is set to n minus 1, which is 3. All right? So that's a step. We come down here, and we say, is k 0? Nope. So then we check if xk is greater than m. So xk is 4.0. Is 4.0 bigger than 5.9? Nope, it's not. So we come down here, we change k to 2, and go back. Now, again, we ask, is k equals 0? This is not. So we come through, and now we check test 7.1, x2 against m. Is that bigger than m? Yeah, it is. So we come through here, and m gets changed to 7.1. And then that takes us over here. K goes down to 1. That's not 0 yet. So we still have to now check 2.3 against m, and it's not bigger. So then k goes to 0. aha, yes, output M. Answer, this is the maximum. All right, so I don't think it was really in doubt, but I wanted to show you, that I understand what a flowchart is. So, now, the main thing that we teach students is to how to, we went through a period where we didn't even teach this, but the main thing we teach students is, how do you know this algorithm is correct? We ran it through one time, but how do we know there's not a bug, something wrong? And so for more than 10 years, people who wrote programs, they just looked at it and said, oh yeah, I know it's right, but they didn't have any particular reason. They just said, I can't make it fail, it must be okay. And so but then Bob Floyd, thank you, Bob, showed that actually we could reason and prove that programs are correct by introducing something called the invariant assertions, and so here we put a little statement saying at this point in the program, it turns out that M is equal to the max of xk plus 1 through xn. And we verify that this is true the first time we come through, and then it's true again every time we go through the loop. So this stays true, and so it's invariant, and so then we know this program actually not only gives an answer, but it gives the right answer. But now, so that's the way it usually is. But as I started writing books on the art of computer programming, I found out that, there's almost always more than one algorithm for a problem. In fact, I'm right now working on volume 3, which is about sorting, and I've got more than 20 algorithms for sorting. And so you need some kind of way to know which algorithm to use, which one's going to be faster, which one's going to use less resources and less memory or something like that. And so that's where analysis comes in of algorithms, where we go beyond proving that the algorithm works to saying how well does it work, how fast does it work, and how much does it cost you when it works. So this is the sort of the underlying theme of analysis of algorithms, kind of quantitative study of the performance of the algorithm, not just the yes or no that it's correct, not correct. Any questions on that? I'm going to analyze this algorithm for you, and you will see. Now, this algorithm doesn't have, there's no issue about how much memory it takes here. It's going to take n cells of memory to store the x's, and it's going to take 2 for m and k, and so that's fixed. Nothing interesting to analyze there, but we do have the running time to talk about. So how long is this going to do? So I'm going to decorate this flow chart with the number of times we come through a particular branch. At the beginning, just once, we start once, and at the end we exit once. So we're coming one time here. How many times am I checking k equals 0? Well, moment's thought, you'd say, yeah, we're actually going to make this test n times. If n is 1, I make the test once, and if n is 2, I make the test twice, and things like this. So this must be n times. Now, so that means n minus 1 times it's coming through here, okay? But then there's a little bit of a problem here. How many times is it coming into this step? So I'm going to call that capital A. That's some quantity that I got to figure out. And on the other hand, it's going to come n minus 1 minus a times through here. You come in n minus 1, go out here a times the other time. The other time has to be n minus 1 minus a. And so there we are. You get this the idea that we have have some quantity A that we have to know if we're going to know how long this program is going to take to run. All right, well, now, okay, so this is the idea. A is the number of times M is changed. Let's, whoops, hey, fortunately I didn't need these. Our job is to analyze A. What can we say about this quantity A? And usually when I analyze something, I set as my goal to find four things about A: the min, the max, the average, and the standard deviation. Sometimes I can do less, sometimes I can do more, but anyway, this is sort of a starting goal. So, in other words, the min this is for optimistic people. What's the fewest times I'll ever need to do it? And in this case, how small can A be? Okay, give me an example when it could be 0. In other words, if you start out already with xn is the max, then we're never going to have to change the max. Okay, so the min is 0. Okay, well, what's the max? How big can A ever be?
N minus 1.
N minus 1, right. We don't have any off by 1 errors here. We have. And what's an example where you're going to need n minus 1? If the example, when they're all in perverse order, they're all, each one is, x1 is the biggest and x2 is next biggest and so on. Okay, so that's n minus 1, okay. So then the average is somewhere between 0, so the max is for the pessimistic people, min is for the optimistic people, the average is for the probabilistic people, and we want to know sort of, realistically, most of the time or something like that, what can we say about typical value of A? It's somewhere between 0 and n minus 1, but is it, maybe half n? Is it maybe square root n or cube root n or something like that? What is actually the average if we do it? Well, in order to define an average, we have to know something about our input. We have to make some assumptions as to what these x's are. If the x's are always the same, then there's no, then the min and max are also fixed as well as the average. So for most cases, it's reasonable to assume that the x's are different. That is, we're never going to have to worry about equality of xi and xj, and that they're in random order. That means that each ordering of the x's is equally likely. So if I have n things that are different and in a different order, then I have n factorial ways in which they might occur. So let's take a look when n equals 3 at what happens. So there are 3 factorial is 3 times 2 times 1. That's 6 ways. And the x's can be like 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. And so let's figure out what A is in each case. We got these 6 possibilities to work on. Each of these 6 is supposed to be equally probable. 1/6 of the time we're going to be faced with them in this order, and so on. Okay, well, so what's A? Okay, so I'm going to put a circle around whenever I have to change M. So to start here at M equals 3, it never has to change. If I start here with M equals 2, I've got to change it here. 3 again, it never had to change. 1, it had to change here to the 3. This 2 had to change to a 3. And here a 1 got changed to a 2, and then that got changed to a 3. So A is equal to 0. It's the number of circled elements here, 0, 1, 0, 1, 1, 2. All right? Well, that's the, so the, in other words, the, if we have the probability that A equals 0, that's 2 out of 6. And probability that A equals 1 is 3 out of 6. And probability A equals 2 is 1 out of 6. Okay. Now we can, from that, of course, we can figure out the average. I might as well do that all. I want to do it slow and easy because we're going to be working a little bit harder later on. But so here we have different probabilities. P0 plus P1 plus P2. It's the sum of these three probabilities. I call this P0, P1, P2. And this the sum of probabilities always equals 1. But then the average is 0 times P0 plus 1 times P1 plus 2 times P2. And so this is 0, 6 plus 3, 6 plus 2 times 1, 6 plus 2, 6. And that comes out to 5, 6. So in n equals 3, we find out that the average value of A is 5, 6. Now let's try to get more general and go to higher values of n. So but I might as well tabulate what we've done so far. I got 2, 3, 1 here, and the and we got an average of 5, 6. Well, I'm not going to worry about that right now. Okay, so what about n equals 4? N equals 4. We got 24 cases. I'm not going to write them all out, but I'll show you schematically what they look like. 6 of the cases start with 1, 6 start with 2, 6 start with 3, 6 start with 4. And so, well, okay, so here it goes 2, 3, 4, 2, 4, 3, 3, 4, 2, 4, 3, 4, 2, 4, 2, 3, 4, 3, 2. And same way with 2, I've got 6 things that, for the guys I've left out, that's 1, 3, 4, 1, 4, 3, 3, 4, 1, 3, 1, 4. I should have done it that way. 3, 4, 1, 4, 1, 3, 4, 3, 1. And 3, it's going to be same kind of thing, 1, 2, and 4, 1, 4, 2. And for 4, it's going to be the same as I had before, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 2, 3, 1, 2, 3, 2, 1. So, it's easy to see then that if we look at what gets circled, that here it's just the same as we had before. We circle this guy, this guy, this guy, and these 2 guys. It's the same pattern. It just added 1 to everything. Same deal here. Sorry. 3, 1. Circled the wrong one. 1, 3, 4. Yeah, this 4 gets circled, and then this 4, and then these 2 4s, and this 3. And so I'm going to get a circle here, and a circle here, and a circle here, and a circle here, and a circle here. And so that carries over just as we had before. But also this one is circled. So now the pattern is clear. Then the value of A is 0, 1, 0, 1, 1, 2. As before, that gets repeated 3 times. And then down here, it gets increased by 1. It's 1, 2, 1, 2, 2, 3. Okay. So then the idea is then that if we add a new element, it's the whole algorithm behaves just as it did before, except if the maximum happened to occur the first time, then we have to bump A by one more. And so so let's write down then P of nk is the number of cases with n elements where A equals k, and a little p of nk is the probability that A equal k is then this capital P nk divided by n factorial. And I wrote the capital P nk here as 2, 3, 1. If I go to n equals 4, how many times do I have a 0 in here? 2 times 3 is 6. So I get 6 times getting a 0 in here. How many times do I get a 1 here? Well, I get 3 times what I had before, plus these 2 1s here. And so that's coming out to be 11. And I get 6 here and 1. So actually, you can see the rule that I used to get this line. I multiply by 3, and then I add the guy to the left. So 3 times 3 plus 2 is 11. 1 plus 3 is 6. 0 times 3 plus 1 is 1. Okay, there we go. Now, when I work on problems like this, we can easily go up now higher. We can multiply by 4 and add the guy to the left, and it looks like this: 24, 35, 10, 1. I always like to also go backward and come back to whoops, 1, 1, and 1. To consider the case n equals 1 and n equals 2. I don't know. Always I catch more when I think of the small case. Generalizing downward has always been an important part of my problem-solving strategy, and so actually I started looking at different algorithms, analyzing them, and fairly often came up with this same pattern of numbers. These numbers started to become familiar to me, and then I learned, oh yeah, a guy named James Stirling had come up with these numbers already in the 1700s, and they're called Stirling numbers. And so now this is something that didn't appear anywhere in my mathematical education. I mean, it was there, and a few people knew about Stirling numbers, but it was just, it wasn't taught. At one point, people saw some use for it, but then it wasn't used much in engineering during the next century or so on. So people started to forget about this stuff. And it was true in general of all the stuff that was going on as I'm analyzing algorithms. I kept finding that I was focusing in on a kind of mathematics that I had hardly ever been taught. But instead, but I had seen it a few times in puzzles or something like that, where the concepts came up. But there was this little part of my math education that had to be amplified, because I was working on topics that arose, the discrete kind of topics that arose in studying algorithms were different from the kind of topics that had been typical in calculus courses and things that had become mainstream mathematics. So I found essentially that my math education was it was great, but it didn't prepare me for analyzing algorithms exactly. And so as time went on, I started realizing that there was this other literature out there, and I could start learning more about Stirling and other people. George Boole actually worked a lot on this kind of problem. And so I decided to add a new course to Stanford's curriculum next fall. So next fall I'm going to introduce a class called Concrete Mathematics, and it should be great, so stick around. Now, okay. The other thing I want to mention is that of course this is a very simple algorithm that we're analyzing, but the techniques that we're using here are techniques that I use over and over again in different ways, and so I realized actually rather early that I would never run out of good problems if I was analyzing algorithms. I knew that there was a whole field called queuing theory that a lot of people worked on, and this was just the analysis of a certain special kind of algorithm. So if I broaden that and say, okay, well, queuing theory was one kind of algorithm to analyze, let me take all the important algorithms of the world and analyze those. I'll never run out of challenging and fulfilling problems to work on. And in fact, there's an extra, not only is it fun to work on these problems, but also when I get the answer, there are people out there who appreciate the answer. So what could be a better way to spend my life? Okay, now let's then proceed further and take a look at these numbers. Well, one of the next steps is to think about these numbers as coefficients of a polynomial. So let's consider a polynomial when I call it 1. Here's 1 plus z, 2 plus 3z plus z squared, 6 plus 11z plus 6z squared plus z cubed, and so on. Now, the reason I do this is because I know that the way that I got from one line to the next was very much like something I do when I'm multiplying polynomials. Because if I look at this polynomial, this turns out to be 1 plus z times 2 plus z. And this one turns out to be 1 plus z, 2 plus z, 3 plus z. Because the rule that I used to get from one line to the next was multiply this by 3 and shift over. That's exactly the same like as saying multiply by 3 plus z. All right. So you can guess what this is going to be factored as, right? And so now we get a formula then. Okay. Then. As I said, I found out that these numbers were identified, called Stirling numbers. So it turned out that P of n comma k is called a Stirling number, n upstairs and k plus 1 downstairs. So actually, I had a closed formula saying exactly what's the number of cases that I'm going to have to change the maximum that many times. Okay, and I also found out that statisticians knew about this stuff, but I think the first statisticians who studied this were in like 1954, something like that. But anyway, they did study what they call record breakers in sports events, and so he wanted to say how many times does the lead change or something like that. So the Stirling numbers came up this way, and then the probability Pnk is then, I have this formula, this divided by n factorial, somehow explaining it. Okay, now I've got a picture here that you can see to show just n gets a little bit bigger. I prepared, whoops. So here's n equals 12. That's as far as I can compute at the moment, without getting numbers that are too big for my computer. But it gives typical results that we can imagine. Here for n equals 12, you see that these numbers these are the capital P's here, and so they get really tiny up here, and they're clustered here. It looks like most of the time we're going to change that maximum two times. So what about when n is 1,000,000? If I'm finding the maximum of 1,000,000 numbers, I'd like to figure out how many times the max is going to change, but it's not. It doesn't look like it's going to be anywhere near like 1/2,000,000. But our next goal is to try to figure out the behavior of this thing as n gets large and see more about what it is. So here comes the great idea called generating functions. So instead of having the formula written out as a Stirling number and everything like that, it turns out to be better to have the generating function, which is which I want to explain. But it was 1 plus z, 2 plus z, up to n minus 1 plus z divided by n factorial. So this is n factorial. And this is equal to the summation of p of k, n comma k times z to the k. So the coefficient of z to the k is this probability that a is equal to k. And it didn't take long when I was working on it, analyzing algorithms, to realize that generating functions were a wonderful way to approach it. Why is that? In fact, this was, of course, discovered 200 years earlier by Lagrange and so on, and Legendre. But I didn't know it at the time from what I had been taught in school. My statistics teacher had talked about something called the characteristic function, which was it turned out to be the same, but z was called e to the it or something like that. I didn't recognize it. So why are generating functions great? Well, most times when we're trying to find average values, we don't know the exact value for p of n and k. We don't have a closed formula for it. Stirling only invented a certain number of numbers, and there's many more problems than there are known numbers. But often from the generating function, we can still find out what we need to know about those numbers, because the generating function is one object, gn of z, while the numbers here are sort of n objects. And so we have generating function is one thing that we can work with and learn about and deduce the p's. So here's the point. Forget n for a moment. Suppose g of z is equal to p0 plus p1z, p2z squared, etc. Then we know that g of 1 is equal to, we plug in z equal 1, and you get the sum of all the probabilities, so this is equal to 1. Next, let's look at the derivative. So I take the derivative with respect to z, and I get p1 plus 2p2 z plus 3p3 z squared, and so on. That's nice, because g prime of 1 is equal to the mean, the average, the expected value of this of these probabilities. It's the sum of p1 plus 2p2 plus 3p3. That's exactly what we said. That's the average. So that's the number we want to get. While I'm at it, I might as well show you the next step, because I did say that I wanted to get the standard deviation as well. So this is 2p2 plus 3 times 2p3z, and so on, 4 times 3p4z squared. And so G double prime is going to be the sum of k minus 1 pk. And if I add g double prime plus g prime, this is the sum of k squared times pk. So, and I might as well go all the way to the next step then, and I get the variance of g, which is the standard deviation squared is by definition equal to the variance, and this is then g double prime at 1 plus g prime at 1 minus g prime at 1 squared. I had to subtract. This turns out to be the well-known quantity by which we measure deviation from. It's the square of the. It's the average value of the square difference of a minus its mean. So that's the indication of how stable the thing is about the mean value. Now the point is, though, that it's really easy to calculate the average of this particular generating function, and the reason is that when we have a product of two generating functions, then the average is just the sum of the two averages. So here I'm going to show you that. That's so nice. If we have a generating function g of z and another generating function h of z, so the product of these two gives you another set of probabilities. And so let's call this capital G. What the heck? No, let me take another one. Say capital G is equal to G1 of Z, G2, well, G and H, that's okay. I'm sorry. It works out that G of 1 is equal to 1. This value is to 1, this value is to 1, 1 times 1 is 1. So all these probabilities do sum to 1. It makes some kind of a probability distribution. And furthermore, G prime of Z is just G prime of Z, H of Z plus G of Z, H prime of Z. And so G prime of 1 is equal to little g prime of 1, and h of 1 is 1, and this one is 1, so this comes out to h prime of 1. Okay, so if we can factor a generating function as a product of other simpler generating functions, then to get the mean we just have to add up the individual ones, and it turns out the same thing for the variance. That is, if I take g double prime plus g prime minus g prime squared, it turns out to be little g prime double prime plus g prime squared plus little h double prime. So the sum of the two variance, the variance is the sum of the two variances. So when you can factorize it, everything becomes simple. Now these then give us the answer to our original question, and so let's see where was I? Yeah. So what do I get for the total? So my generating function was 1 plus z over 2 times 2 plus z over 3, and ended up with n minus 1 plus z over n. Each of these is a generating function by itself, and the average of this one is 1/2, this one is 1/3, this one is 1 over n, n. Right, this is, I mean, you take the derivative and evaluate it at 1, and so you get 1/2, 1/3, so on. And so the sum of these is the average, except that, okay, so now here, this turns out then to be the harmonic number minus 1. The harmonic number h sub n is defined to be the sum of the first reciprocal starting with 1 instead of with 1/2. All right, so the answer is then hn minus 1 here, and the standard deviation works out to be the square root of hn minus the second order harmonic number, which is the sum of the squares of the like 1/2 squared plus 1/3 squared, 1 over n squared. So these are the sort of, this answers the original question, saying that the average turns out to be this harmonic number, which then we get to know is very much like the logarithm. And if n is 1,000,000, it turns out to be about 13.5. So okay, so that's the. So it tells you that we're not going to be changing the maximum very much often in a million time. And once again, this quantity h sub n, harmonic number, was appearing in zillions of different algorithms that I was studying. So even though, as I'd been a math student, I'd run into the sum of these reciprocals maybe half a dozen times somewhere in my education, all of a sudden I realized that if I was going to be analyzing algorithms, I'd not only have to know about hn, but I'd have to know how to calculate the sum of k times h sub k, and I'd have to know how to calculate the sum of hn squared and all kinds of things. I had to know all kinds of things about these numbers hn that I hadn't been taught before. And that was because the computer applications were telling me, you know, this is a part of mathematics that I really could have learned if it hadn't faded out of history. So that's why I'm going to try to teach this course, concrete math, next fall. That brings us into the curriculum. From a practical point of view, now I've analyzed this algorithm. What does that tell me? About suppose I'm writing a compiler. Does that tell me something about how to arrange the code? Well, in the first place, I actually I already made the first simplification. When I presented the algorithm, I started out with k equals n minus 1 instead of starting out with k equals 0, or without starting out. I could have started out at k equals 1 and go up and go and say this k equal n here. And well, I knew that a computer was easier to test for 0 than to test for n. And since I'm doing this every time, I wanted this test to be as simple as I could. So I already biased that when I wrote the program by counting downward instead of going up. But then the analysis tells us that almost always we're going to come down this branch, and hardly ever are we going to be tricking around in here. So what the computer is going to be spending its time going zip, zip, zip like this all the time. And so this will tell us not only that, well, we should arrange the programs, the instructions in memory so that this path is nice and the computer goes as fast as it can zip on these instructions. But then when it has to make a side trip, then we don't really care so much about what it does to fix up. And even more so, we realize that we could double up on this loop, and we could combine several values of k. We only have to test to see if k is getting small. Say, is k bigger than 5 or not? And if not, then we can do 5 of these tests right away without making separate tests each time. And so next summer, I'm going to be running a project where I want about a dozen volunteers to go through and see what programs people are writing at Stanford and we're going to scour the waste baskets and look at, get source code from wherever we can and see what people are actually doing in their programs, and we're going to analyze how much a compiler could do by we're going to take a look at the bottlenecks in the programs that we find around, and we're going to try to empirically figure out how often we can make a big improvement over what the compilers do now. So I'm looking for volunteers for this summer project. Okay, now how are we doing on time? Okay, good. Then I guess it would be time for me now to say what's the takeaway. Except in 1969, I wouldn't have said that because that's a modern phrase. But anyway, what do we get out of this? First of all, I wanted to show you that by trying to use mathematics to find quantitative things about computer programs, we had a new dimension to what we knew before about programs. Secondly, I wanted to show you that the techniques are they have some kind of a system to them. They feed on each other. You can each program doesn't have its own special trick, but these things. It turns out that there's that we begin to learn a discrete calculus that was analogous to the infinite calculus that we've been taught, and I wanted to show you that it's enjoyable to psych out these problems, and so I believe then that I can safely say that I've got more than enough for one lifetime's career ahead of me of pleasant applications that combine traditional mathematics with efficient use of computers. Okay, thanks a lot for listening. Are there any questions?